All right, so here's a review for Unit 9 on electrical charge, force, and field. Um, First off, well, I've got the test in front of me, so I'll be kind of looking through there, making sure we're hitting all the ideas that are there, as well as the notes that I'll kind of scan through and talk about some things. Probably won't do many calculations, but I'll talk about some of the things we need to be able to do. I probably won't do them because you all know how to plug into an equation. You're good at that. First idea here, Benjamin Franklin said there were two types of charge, positive and negative. He realized that because charged objects could either attract or repel, in order for that to happen, there had to be two types of charge. So objects with the same charge repel each other, and objects with different charges attract each other. So positive and positive repel, negative and negative repel, but positive and negative will attract each other. One of the big ideas that will have sort of overarching everything is this idea of conservation of charge. If we have so the idea of net charge being closed, and the net charge in a closed system having to remain constant, that's going to guide us when we start talking about charging objects and working with charges on objects. This idea that if we have a closed system, if we're not grounding anything, whatever charge we start with has to be what we end with. So here, just the idea of an atom. We have the nucleus with the protons, and those protons are locked in. We're not ever going to move any protons. We are only moving electrons as we do these problems. Instead of moving the protons, we're moving electrons. And if we have a neutral object, realize that these neutrons don't matter at all. If an object is neutral, we get charges from the positive that have to balance out with the charges from the negative electrons. The idea of conductors versus insulators. Conductors allow charge to be passed through. Insulators, not so much. And realize that on both of these, the protons are locked in. Protons do not move, but the electrons in a conductor are free to flow. A large idea here is the idea of quantized charge. The lowest amount of charge that we can pass is the charge that is on an electron or a proton. Really, we're transferring electrons, but the smallest amount of charge you can have is what is called an elementary charge. It's the charge on an electron or a proton. Electron is just negative E, and a proton is positive E. 1 coulomb is the unit that we use for charge, and an electron is 1.6 times 10 to the negative 19th coulombs. Conversions here, let's say you had a problem that gave you a certain number of protons, neutrons, and electrons. To find the number of elementary charges, you only worry about the protons and the electrons. So we've got 20 positive elementary charges from the protons. Neutrons don't matter because they are neutral. And 18 electrons, so 20 minus 18, then subtracting the 18 because it's a negative elementary charge, leaves us with a net of 2 elementary charges, and then we do a conversion. If we're converting out of electrons, we want to put the elementary charge on the bottom, and then the coulombs that we're trying to get into on top. So notice, as we go from 1 electron to 2 electron, we jump from 1.6 times 10 to the negative 19th to 3.2 times 10 to the negative 19th. It's impossible, you cannot do it, get a value of anywhere in between there. If a problem mentions that, let's say it said that someone did an experiment and they got a value of 2.5 times 10 to the negative 19th coulombs. Something went wrong in their experiment. You can only transfer electrons. So if you do not have a whole number multiple of electrons, something is wrong. So be aware that the smallest amount is this value, the 1.6 times 10 to the negative 19th. And any value we get has to be a whole number multiple of that. Same sort of stuff, just again scanning through here. All the same stuff. So to make something positive, we're going to remove electrons, and to make something negative, we're going to add electrons. Same idea, we don't move any protons, we only move electrons. So the idea of conservation of charge. Whenever we have objects that are identical and they are uh, conductors, identical conductors and spherical, they've got to be sphere shaped for this to work. Uh, if we touch them together, we split that charge evenly between them. So here we started with a charge of Q, and we touch it to a charge of 0, an uncharged, a neutral. So both of those two got Q over 2, or a half a Q. That still adds up to be Q, right? That has to be true. Half a Q plus 0 still adds up to Q. And then again, we touched the second one now to the third one, and we still add up to Q. We don't lose any of that charge. We have to keep the same amount. So now we're moving into the idea of Coulomb's law. This is the sort of the main equation we got for this unit. Things to be able to do. Make sure you can solve for any of the variables present. Again, you will be given this Coulomb's law constant. It's on the green sheet. And realize that there are a lot of parallels to the gravitational law, Newton's law of gravitation. The differences are we're using mass instead of charge, or now we're using charge instead of mass, but they are both still r squared or inverse square laws. So if you double the distance on a either two masses or two charges, both of them result in the exact same change. If you double the distance, you end up with a fourth of the force present. They both rely on this sort of 1 over r squared piece. Those are analogous. They're the same for both of them. And that is the distance between the centers still. It's not a radius or anything like that. Differences again, gravity is always attractive. Electricity is attractive or repulsive. But gravity wins on the big scale. When we get up to large objects, typically those objects will negate themselves electrically. So when we get very large objects like planets and stars, they attract other charges, but then those charges end up balancing out until they become overall neutral. But as they come together, we still end up getting more mass, and with gravity, it just keeps adding on and on and on. We're not, losing any of that charge. So here with gravity, it wins on the big scale, but electricity, smaller scale, is going to be much more relevant, a larger magnitude on the electric force. So things to be able to do with that equation, solve for it, be able to tell what direction a force is acting on one of those charges, and realize that the force on both charges is equal, but it is in an opposite direction. So Q, let's say Q1 there is attracted to Q2, they will have the same force. Let's say it's 10 newtons, but one will be to the left and one will be to the right. Again, if we want to make the force bigger, we can either increase the charge or make the distances closer together, decrease the force, decrease the charge, and increase the distance. The farther away you are, the less the force is. As you do these problems, I would suggest maybe drawing a little picture to keep everything straight. Some of the battle with these types of problems are just keeping all of the directions straight, making sure that everything stays where it needs to be. Every once in a while, we'll see a problem with 3 of these spheres, 3 of those charged objects. To solve these, just solve the force between 1 and 2, and then 1 and 3, and then 2 and 3. You end up with all 3 of these forces, and I notice that as I solve these, so for 1 and 2, we got 198 newtons. That is the force acting on both charge 1 and 2, but since they are both positive, they repel, so this charge here is pushed to the left, this charge here is pushed to the right. So I do that for all of them. Then if I want the net charge on one of these, let's say I want the net charge on the sphere number 1, I've got 11,655 newtons to the right, I've got 198 newtons to the left. I subtract those two, and my net is to the right because the right has more force to start with. A couple more examples, same sort of thing. me scan through all these notes, make sure I'm not going through some of the same stuff again. So when we deal with electroscopes, and I think I might switch to a different, oh, here we go, these are good. So when we talk about electroscopes and this idea of separating charges from one another, we always want to look what's happening to the electrons. We can create this charge separation if I bring a positive object close here. All the electrons inside here are going to get pulled towards that side, so I'll have a side that is negative and then this left side that is positive. So when we want to charge by conduction, this is where we have contact. Bring an object in contact and then separate the two objects. Things to remember here with conduction is that whatever charge you bring is now going to be the charge on the electroscope as well. And whatever you brought is going to lose a little bit of its charge. It has to use that up. It's sharing that charge. And remember, it's always only electrons that are moving. Even if we gain a positive charge, it's because electrons left an object. It's not gaining any electrons from the other it's not gaining any protons from the other object. Charging by induction is where we charge without touching something. And in order to do this, we have to ground and unground the electroscope. When we do that, when we ground the electroscope, we sort of either push off or bring on extra electrons. And when we unground it, we sort of cut that connection off. So we either added some electrons or we took away some electrons from the electroscope. This is a situation where it's not a closed system. So we are going to get an actual change in the number of electrons, the amount of charge that's present in our system. Things to remember, the charged object doesn't get changed at all. If I bring a negative object, it still remains negative and just as negative. Electroscope now has the opposite charge, so if I bring a positive object close to the top of an electroscope, those electrons are going to, so if I brought a negative object, that will push the electrons down into leaves. When I ground it, those electrons will rush off, leaving me with a more positive object because I now have less electrons. And the ground is really the source for all of that. A couple of quiz things here. Let me see if there's anything else. And the last thing with the electroscopes is just to realize that no matter what type of charge you have, whether it's positive or negative, if you bring it close, those leaves separate. So leaf separating only tells you that there is a charge. It does not tell you what type of charge it is, because if I bring a positive charge close, that's going to push electrons down into the leaves and they'll separate because now they're both negative. Or if I have a negative object and I bring it close, the electrons will run up. Let me say that again, because I think I'm just messed that up. If I bring a positive object close, the electrons run up to the top, leaving the bottom, the leaves positive. They separate. And then if I bring a negative object, the electrons push down, which makes both the leaves negative, and they still separate. Sorry about that. So again, the main idea there is that the leaves diverging only tells you that there's a charge. It doesn't tell you what type of charge is present. Last thing we had was the idea of the electric field. Most of this will be sort of calculations based. This equation here, E equals F over Q, is going to be your best friend for that. And a couple things with this, realize that the direction of the field is the direction of a force that a positive charge would experience. We're always dealing with the force that a positive charge would experience. So in this case where we've got a negative, it tells us the field is to the right based on those arrows. So because the field is to the right, it then experiences a force to the left. Because it is a negative charge, it experiences a force in the opposite direction. If this was a positive charge, then it would also experience a force to the right, but it is not. So when we switch those charges, so if I switch it just to be positive, it would experience the same amount of force, but it would just experience that force in a different direction. Again, be able to do those calculations. They're very simple. They will be straightforward just like that. And last but not least, This will be a little bit shorter of a video. It wasn't a very long unit. And for the most part, we covered everything today. Electric field lines point out of a positive charge, because if I put a positive little test charge here, it would go away. So the field line would point outward. And for a negative charge, it points inward, or it terminates at the negative charge, that field line, because if I put a charge here, it's going to go right into that negative. And if I put one here, it's going to go up and around into that negative. Let's see, what else, what else, what else, what else, what else, what else, what else? Doesn't look like too much. Let me switch over to the test practice problems. I'll just kind of run through some of these. Again, we ran through these in class, but again, converting into between coulombs and elementary charges, counting those elementary charges if you are given protons and electrons, and getting those into coulombs. Realizing that you have to have a whole number multiple of elementary charges, so convert this coulombs into elementary charges. If it's a whole number, we're all good. If it is not, we're all bad. Knowing how to charge an electroscope by induction as well as by conduction. Here, the electrostatic force, repulsive. It can be attractive sometimes, as long as positive or negative. The gravitational force is always attractive. Two forces mentioned has a greater magnitude. Because we're working on the small scale, relatively small kilograms, our electrostatic force is going to be much, much bigger. And the distance cut in half. So if we take a look at that equation, that F is K Q1 Q2 over R squared. K, Q, and Q are all going to stay the same. So we'd put sort of ones in for there in the equation. But as the distance is cut in half, it would be 1 over 1/2 squared. So 1 over a fourth, which is 4 times. So our electrostatic force would be 4 times as big. Gravitational force, the exact same thing would happen there, because the electrostatic and gravitational force are both reliant on that R inverse square of the distance. Being able to calculate both of those, you can show it more specifically which one's bigger. Calculate for a charge, realizing that the force has got to be equal going out of this one. The forces between them will always be equal but opposite. So we'd have 1.2 newtons to the left. Here, calculate for the distance between the two. Because the distance is a squared value, make sure you take the square root at the end. Make sure you're double checking your algebra. Here, one of the 3 problems, being able to calculate and keep track of all those variables and values. Some separation stuff. Identical conducting spheres means that when they touch, they're going to split whatever charge is between them equally, but the total amount of the charge for the system remains the same. Whatever it starts out with is going to be constant throughout. Working with some field stuff, realizing that if you get the force that's exerted and you know the mass, the acceleration is a result of net force equals ma. And also realizing, kind of back up here with some of these, if I was to ask which of these two would experience a greater acceleration, but if it was, well, let's actually go back to a different one. So one like this, which experiences the greater acceleration? Be careful. For this particular problem, there's absolutely no way to know. Charge and mass are not the same thing. So just because this one here on the right has less charge does not mean it has less mass, and charge has no effect on the acceleration. We're only worried about the mass and the acceleration and the force, F equals ma. So be careful. If it asks you about acceleration, make sure you use a mass in that equation or to solve for that. And that's relatively it. Kind of like we mentioned today in class, just be careful of little things. Make sure you're including your micros and your millis. Make sure everything's getting plugged in the right way to your calculator when you're doing a exponent or a times 10 to the -6, -3, that you're putting that in parentheses so that the right stuff gets multiplied. And just take your time. Again, this is a very straightforward test. I don't imagine it will be that difficult for most people. But I hope this helps you in getting ready. If you have any questions, just send me an email. I'll be around all weekend to answer those. But I hope you all have an enjoyable weekend of studying and of fun. Have a good one.